Hi folks, welcome back to AP Stats. This is Mr. Robeson here. We are starting to look at something called confidence intervals today. This might be a long one, so I'll try and go quick if I can. All right, so first up, if we were going to estimate the proportion of Hershey Kisses that land on the base, what would we do? Most people would just guess a number. Maybe like 33% or maybe 30% or 40%, 50%, whatever. Estimate the average date on a penny from Mr. Robeson's collection. So we saw then in one of the other presentations that it looked like it was 1999 was the average date. Most people would just guess one number. All right, estimate how many M&Ms are in an average package. You know, if we had class, we would have seen that it's probably somewhere around 50, maybe 60, 55, whatever. But all these guesses are what we call point estimates, all right, because we're guessing just one number at a time. And usually we're guessing a population parameter. We are trying to estimate the population parameter with one number. And that is what's called a point estimate, because we're guessing one point. All right, now, generally this doesn't work so well. Like, the chances that we're going to be right exactly are almost nothing. All right, but we try and guess. All right, a better way to guess, though, would be to guess a range of numbers. Like, it's between 50 and 60 M&Ms in a bag. The date is between 1995 and 2005. All right, so we can do that instead. That's where confidence intervals come in. All right, so all this guessing, so using a sample to predict something about the population, that is inference. That was our fourth domain of statistics, and that is what we're looking at here with confidence intervals and with point estimates. All right, so a little bit of point estimates. So let's see. We want to know how long AAA batteries will last. We take a random sample of 12 batteries and test how long they last an hour. So this is how many hours each of those 12 batteries lasted for. So what should we use for the point estimate? For the population mean. So again, this was sample data, and we want to know what the population mean would be. We want to estimate it. Well, we could pick any one of these numbers and say, well, 17.5, that sounds good. Or I can look and be like, well, it looks like there's more 16s than 17s, maybe 16.5 would work better. All right, the best thing to use is to use the sample mean. X bar. All right, because we've got data, we might as well do some number crunching on the data, find the statistic, and we use the sample mean. All right, what should we use to estimate the population standard deviation? Well, same story. We should use the sample standard deviation. Which we use the letter S for. All right, so these are both point estimates because we're going to guess just one number. That's it, just one number. All right, same here with proportion. What proportion of U.S. adults consider themselves vegetarian? The Pew Research Center survey reports that of 1,473 randomly selected adults, of these, 124 said that they were vegetarian. So our guess, what we would use to guess P, is we say it's approximately going to be whatever P hat is from this, which is the 124 that said they were vegetarian out of 1,473. All right, so we use sample data to guess the population data. All right, but a better way to guess, so better than just guessing, is to guess an interval. All right, so we have a better chance of getting the number right because we're basically getting multiple guesses. All right, we're basically cheating. I mean, it's like saying, hey, pick a number between 1 and 10. And you say, okay. It's somewhere between 1 and 10. I'm not wrong, right? It's cheating, but it works. And we do this in statistics all the time. So if we're using a sample distribution and the sampling distribution is normal, which is why we always check to see if it's normal, then the empirical rule works, which means approximately 95% of the sample means will be within 2 standard deviations of the population mean. So we could start from our mean, and we could go up 2 standard deviations, and we could go down 2 standard deviations. And technically, we don't have this mean. We'll have X bar, and that's what we do usually. All right, so we go up and down 2 standard deviations, and we should capture the mean. So somewhere in between here, like maybe here, was the mean. So the sample mean was not exactly the population mean, but we should capture it somewhere in this interval that we make. Or at least we should 95% of the time if we go about 2 standard deviations. All right, so here's an example We have normally distributed. From the last slide, we got that the mean was this, the standard deviation was this. We were using a sample size of 12. How can we be 95% confident of guessing the population mean lifespan? All right, well, we would make a confidence interval and we would go up and down 2 standard deviations. So we'd have 16.45 minus 2 times whatever we're using for our standard deviation. And then we would go up to 16.45 plus 2 times whatever we use for our standard deviation. Now, we're usually working with a sampling distribution instead of just this distribution, so we'd actually be dividing by the square root of n. So that's what's coming up next year, is later on we'll be dividing by the square root of n. But that's how we would do it. All right, we'll work on more with this actual formula later. I'm just kind of showing you the main ideas right now. So we subtract 2 standard deviations, add 2 standard deviations from the mean that we have, which is our sample mean. All right, so we end up making what's called a confidence interval. So it is an interval of plausible values. So every value in there is a plausible value for the parameter. So the population mean or the population proportion for mu or p. All right, based on sample data. All right, each value in the interval is just as likely the population parameter as any other. So if it's on the edge of the interval, that's fine. It's still in the interval. It's not like closer to the middle of the interval is better anymore. It's just, if it's in the interval, it counts. All right, and the way we interpret a confidence interval is we use this exact same sentence just over and over and over again. We are 95% confident or 90% confident. We'll have this. They'll give us this. That the interval from the smaller number to the bigger number, and we just say what the numbers are. We can put the units there if there's units too. Captures the, and then we say what we're trying to capture. The true mean, the population mean, the true proportion, the population proportion. So we can use the word true or population interchangeably. All right, and then we come to confidence level. So this is our level of confidence. So when we're making a confidence interval, they'll give us ahead of time what level we want. It's this percent down here, C percent. Right. It gives the overall success rate of the method used to calculate the confidence interval. That is, in C% of all possible samples of size n, the interval computed from the sample data will capture the true parameter. So if we get a 95% confidence interval, 95% of the time when we make a sample of size n, it should capture the population mean, which would be mu or population proportion p. Right? That's what we're trying to guess, is the population information. Parameters. True parameters. All right, to interpret the confidence level, we just say this sentence. If we were to repeat the same process 100 times, or many times, we could do either way, we would expect C, like 95 out of 100, or C%, if we say so many times, of intervals to capture the population parameter. The population mean or the population proportion. We could also use the word true mean or true proportion, but we are talking about population, not sample. If we use the word sample there, it's wrong. All right, so I used a simulator here online. There's a link to it at the end of the notes here. And we can take a mean of mu, and we have a sampling distribution of all samples of certain size n that had a mean of mu from the population. And we made all these confidence intervals. And I believe these were 95% confidence intervals. And if we look at this, 95% of them, all the green ones, they hit it. They captured the true mean. This is our true mean right here. One of them missed it, which is what we would expect. 95% would get it. One sample was not a good sample, but it still works. I mean, it's still a valid sample. All right, so if we took different samples, we would get different means in different proportions. Each of these sample means and each of these sample proportions is a point estimate. If we make a confidence interval, we add or subtract the margin of error to each one of those, like the point estimate plus or minus the margin of error. And then we make this interval. We use interval notation. So we use parentheses on the edge. All right, so each of these red dots is a sample mean. And the green is our margin of error added and subtracted to each one. All right, so here's an example. We just want to answer these couple of questions here. So 2 weeks before an election, a polling organization asked a random sample, good, gotta be random samples, of registered voters, if the election was held today, would you vote for candidate A or candidate B? Based on this poll, the 95% confidence interval for the population proportion who favor candidate A is 0.48 to 0.54. So interpret the confidence interval. All right, so this goes back to our sentence. So our sentence is, we are 95% confident that the interval from, and now we say our lower value to our bigger value, from 0.48 to 0.54 captures the true proportion, or we could say population proportion, of, let's see, who did we sample? Registered voters. So we could just say of voters who support or who favor candidate A. All right, so there's our interpretation of a confidence interval. Next up, all right, it's always the same sentence. Interpret the confidence level. All right, so if we took, I'm going to go with the many samples. Doesn't say the sample size, does it? So of the same size, we would expect, and let's see, what percent are we? 95. 95% to capture or contain the true proportion of voters who favor candidate A. I'm just going to say A. All right, so there's our confidence level sentence. All right, what is the point estimate that was used to create this interval? All right, so the point estimate would be the middle of the interval. So we need to find what's the middle of the interval. So to find that, we could just average those two numbers. Or we could subtract and find the difference and do, there's a bunch of different things we could do, but we could just do 0.48 plus 0.54 divided by 2. I believe it gives us 0.51. That was our point estimate. That was the p-hat we used to estimate that interval. What's the margin of error? Well, we can do a couple of things here. We could go from either end. It could go 0.51 minus 0.48 gives us 0.03. There's our margin of error, or ME. We could also do 0.54 minus 0.51, should give us the same thing. There's our margin of error. Or, if we didn't have this first, we could just do 0.54 minus 0.48, which gives us 0.06, and divide it by 2, because that's two margins of error. One's going up, one's going down. So there's our margin of error. So we got 3 different ways we can calculate it. All of them give us the same answer. All right, and finally, based on this poll, a political reporter claims that the majority of registered voters favor candidate A. Evaluate this claim. Well, it looks like anywhere from 48% to 54% favor candidate A. So it could be 48%. That's not a majority. Or it could be all the way up to like 54%. And I realize some of you in calculus are like, well, it can't be the endpoints. Well, it could be 48.000001. Right? We're not too picky about the interval endpoints. We could also use brackets for those of you that are in calculus. It doesn't make much of a difference. We always just use parentheses. That's our normal notation, which is a majority. All right, so is it safe to make the claim that the majority of voters favor candidate A? No. It could be 48. Which is less than a majority. Remember, any point in this interval is a plausible value. And any point in that interval is just as plausible. Doesn't matter if more of the interval has 50%. Any point in that interval will count against it. All right, so let's see. What affects the margin of error? All right, so the confidence level is the first thing. So we really only have two things here. So if the confidence level increases, so as C increases, the margin of error also is going to increase. The more confident we are, the bigger interval we're going to make. Like if I said pick a number between 1 and 100, and you said, 50. Well, you're not going to be very likely to get it. But if you pick a bigger interval, say 50 to 60, now you're more likely to get it. If you pick a really big interval, like 1 to 100, you're 100% likely to get it. All right? So the bigger the interval, the bigger the margin of error, the greater the confidence level. So as the confidence level decreases, the margin of error also decreases. And the other thing that can affect the margin of error is the sample size. If we pick a bigger sample, so as n increases, our margin of error is going to get smaller. So the bigger we get for a sample, the better for the most part. As n decreases, if we pick a small sample, then our margin of error is going to be larger. We're going to be less likely to be confident about it. All right, so far we've only used the 95% interval. That's all we've talked about, which was roughly 2 standard deviations. We'll learn later it's 1.96, but it's roughly 2. But this number, how many standard deviations we go, that is what we call our critical value, or a critical point. So we'll start with our statistic, which would either be x bar or p hat. We'll have a critical value, which we're going to use z star for, and we'll have our sampling standard deviation, or something equivalent to it. And that's how we're going to end up making these intervals. All right, hopefully we can get through this one. So explain one potential problem with the size of the sample. So let's see, part of our project about response bias, Ellen surveyed a random sample of 25 students from her school. One of the questions in the survey required students to state their GPA aloud. Based on the responses, Ellen said she was 90% confident that the interval from 3.14 to 3.52 captures the mean GPA of all students in her school. So what's one potential problem with the size of the sample? Well, the size of our sample is 25. Think back to our Drake mean. Drake did not like 25. 25 is less than 30. So the CLT does not apply. In other words, we don't know if it's normal or not. We don't know if our sampling distribution is going to be normal. So that is a problem. All right, so it could not be normal, and then we wouldn't be able to make the interval. Explain what would happen to the size of the interval if the confidence level were to increase. So if confidence level increases, the interval size, or actually we said the margin of error increases, which means the interval will be larger as well. How would a 90% confidence interval based on the sample size of 200 compare to the original 90% interval? So now we've got n increasing. So if n increases, then we say the margin of error gets smaller. The better we sample we get, the smaller margin of error, which means our interval size, ZE, will also get smaller. Smaller margin of error, smaller interval. So instead of going out like this far in each direction, we'd only go out this far in each direction. Smaller interval. Describe one potential source of bias in Ellen's study that's not accounted for by the margin of error. Well, she asked students to state their GPA. So students might not remember. Or know their GPA. All right, so that means they're probably doing some sort of response bias. Or maybe they could lie, which would also be response bias. So there's a couple of different ways we could have bias there. All right, and that's it. Tried to keep it under 20 minutes. Sorry if it's a little long, but that is our introduction to confidence intervals. The next one we'll actually go over how to make them, and we'll use the calculator to make them and what conditions we have to check.